everyone. We are here to present our research on hybrid face iris biometric authentication using cross deep learning models. The goal of the study was to develop and optimize a multi-model biometric recognition system using face and iris features. Our team consists of me, Dhruv,
I'm Avni.
I'm Hanzala.
and Garv.
and we will walk you through the methodology, experiments, results, and conclusion of our work. Biometric authentication is crucial for security and identity verification, with face and iris recognition being two of most widely used modalities. However, unimodal systems suffer from limitations such as vulnerability or spoofing attacks and environmental challenges. Our study explores the potential of combining face and iris recognition in a multimodal system. To overcome these limitations, we aim to demonstrate how fusion techniques can improve accuracy, robustness, and reliability.
The main research problem we address in this work is the challenge of class imbalance, especially the disparity between genuine and imposter pairs in biometric datasets. We also explore how effective fusion techniques such as cross attention and score level fusion can improve multimodal performance. Our study focuses on overcoming these challenges by developing a refined multimodal system that addresses class imbalance while maximizing fusion accuracy. Our motivation for this research stems from the growing need for more secure and accurate biometric systems. Single modality systems such as face or iris recognition alone may not be robust enough to handle varying conditions such as lighting, orientation, or partial occlusions. By combining face and iris features, we hypothesize that system can achieve higher accuracy and robustness compared to unimodal systems.
Now for the objectives. We approached this problem by developing three experiments or approaches. In the first approach, we compared face only, iris only, and multimodal recognition using a balanced data set. In second approach, we introduced class weighting to address class imbalance, resulting in improved performance. Finally, in the third approach, we focused on optimizing multimodal performance, achieving a high accuracy of 98%, but also highlighting the challenges of dealing with imbalanced data. Now, for the baseline comparison, in the first approach, we aim to establish a baseline comparison by evaluating the performance of face only, iris only, and multimodal systems. We used a balanced data set where genuine and imposter pairs were evenly distributed. We tested different architectures, including ResNet 50 for face feature extraction and ResNet 34 for iris recognition, and used a simple cross attention fusion technique to combine these modalities.
In second approach, we refined the multi-model system by introducing class weighting to handle the imbalance between genuine and imposter pairs. We also adjusted the negative ratio to control the proportion of imposter pairs in the training set. This approach utilized ResNet 50 for face feature extraction, VWG16 for iris feature extraction, and cross attention fusion. We saw significant improvement in accuracy and F1 scores with this approach. In third approach, we focused on optimizing the multi-model system by using the best fusion techniques and architectures. We continued to use ResNet 50 for face recognition and VWG16 for iris recognition. However, we applied more advanced fusion techniques including cross attention and score level fusion to achieve high accuracy of 98%. Despite this, the system showed weakness in handling the minority imposter class, which led to poor precision and recall for imposter pairs.
Our dataset was the Visa multi-model dataset, which consists of face and iris images. We performed pre-processing steps, including resizing the images to 224 into 224 pixel and normalizing the pixel values between 0 to 1. For data augmentation, we use techniques such as random horizontal flipping, random rotation, color jittering for the face images, while iris images were treated as grayscale inputs.
Now, for the model architecture, the face feature extractor. For the face feature extractor, we used ResNet 50, which is known as its deep architecture, and which has its ability to extract high-level features. We modeled the final fully connected layer of ResNet 50 to output 512 features. Now, this enabled the model to focus on the most relevant features for biometric recognition and enhanced its ability to generalize. Model architecture for the iris feature extractor was for the iris feature extractor, we initially used the ResNet 34 in approach 1 but switched to VGG 16 in approach 2 and approach 3. VGG 16 was modified to accept grayscale input by adjusting the first convolution layer. This adaptation allowed the model to better handle the unique characteristics of iris images such as high frequency patterns and fine details.
Next, we have the fusion techniques. Fusion is a key to multimodal systems. In our work, we use two main fusion techniques. First, in approach 1, we applied a transformer encoder for cross attention fusion, where face features and iris features were processed with attention mechanisms to focus on the most informative parts of each modality. In second approach, we combined cross attention fusion with score level fusion, where the outputs of the face and iris classifiers were concatenated and passed through a feed forward network. For training, we use the Adam optimizer with a learning rate of 3e minus 4 and a batch size of 16. The number of epochs varied across approaches: 10 for approach 1, 20 for 25 for approach 2, and 4 for approach 3. We applied cross entropy loss in all approaches, but in approach 2, we introduced class weights to handle class imbalance. The model was trained on a GPU to accelerate the computation.
Evaluation metrics. To evaluate the performance of our models, we use several metrics: accuracy, precision, recall, F1 score, and ROC AUC. Accuracy measures overall classification performance, while precision, recall, and F1 score provide insights into class specific performance, especially important when dealing with imbalanced data. ROC AUC was used to assess the model's ability to distinguish between genuine and imposter pairs. Results of approach 1. In approach 1, we observed that the multimodal model outperformed both face only and iris only models. The multimodal model achieved an accuracy of 58%, while face only and iris only models achieved accuracies of 52% and 42% respectively. These results highlight the potential of multimodal systems in improving accuracy. The confusion matrix for this approach showed that the multimodal model was more consistent across different types of pairs. In approach 2, with class weighting and adjusted negative ratio, we saw significant improvement in the performance. The multimodal model achieved 80% accuracy with better F1 scores compared to approach 1. The face only model was also improved to 77%, while the iris only model still performed poorly at 25%. The confusion matrix showed a more balanced performance across the classes, and the ROC curve further confirmed the improved generalization.
For the results of Approach 3 achieved the highest accuracy at 98%, but the performance on the imposter class was poor, with precision and recall close to 0%. This imbalance, with only 5 imposter samples compared to 219 genuine samples, led to misleadingly high overall accuracy. The confusion matrix showed that the model predominantly classified genuine pairs correctly but failed on imposter pairs, indicating the need for better handling of class imbalance. Here, we compare the accuracies and losses across all approach. The multimodal system consistently outperforms the single modality systems in the terms of accuracy. We can see that approach 2 with class weighting provided the best balance between accuracy and F1 score. However, approach 3, despite its high accuracy, suffer from poor performance on the minority imposter class. The comparison underscores the importance of balancing class distribution.
Now, for the conclusion, our study demonstrates that effectiveness of multimodal biometric systems with the fusion of face and iris features significantly improves the performance over unimodal systems. Now, approach 2 with class weighting and adjusted class ratios achieved the best balance between accuracy and F1 score. However, the approach 3 that we used showed that high accuracy can be misleading when class imbalance is not addressed. Future work should focus on larger data sets and explore alternative fusion techniques to further optimize this performance.
Looking ahead, we plan to experiment with larger datasets and real world scenarios to improve the robustness of the model. We also aim to explore alternative fusion techniques such as core level fusion in greater depth. Additionally, we would like to thank our advisors and the research community for their valuable insights. Thank you for your attention, and we are happy to answer any questions.
Thank you.
Thank you.
Thank you.